I want to talk a little bit about Thevenin and Norton circuits. They're really important. So, of course, the Thevenin and the Thevenin circuit and the Norton circuit, they're interchangeable. They're equivalent, totally equivalent, and they're really, really useful ways to think about things. They're good ways to solve circuit problems, and they can give you a lot of insight. Of course, this Norton current can be found as IN. It's just equal to, by Ohm's law, the Thevenin voltage over the Thevenin resistance, and or that would be VTH over RN. I'll just usually say RTH, and you can go back the other way. You can find that VTH is just equal to IR IN times RTH. They go back and forth. They're massive simplification. They make things much easier for you. And this course really isn't about solving circuits. So you've learned methods like node voltage and mesh loop, and maybe you like them, and they're good. They work well. But they don't give you much insight about what's going on. They're good ways to solve circuits, but they're not good ways to understand circuits. And you probably want to understand the circuits. I want you to understand the circuits. And the insight you get from Thevenin and Norton circuits is much better. Now, amplifiers, which is basically the subject of Electronics 1 and Electronics 2, although it'll take us a little while to get to there. Amplifiers often have a voltage in and a voltage output. But transistors are actually something more like a Norton circuit. BJTs, bipolar junction transistors, and MOSFETs really act like a voltage-controlled current source, and often a Norton circuit is the better way to represent an amplifier. Yet when we're building an amplifier, we're looking for voltage in and voltage out. So you often would use a Norton circuit to represent the transistor, but that's inside an amplifier, which we're really looking at as a kind of a Thevenin circuit. So it's pretty useful to understand them and to be able to just convert back and forth without any question or time. Just immediately see it and just do it. So how do you find these? How do you solve circuits like this? So I like to think about opening up a source and to find the circuit's equivalent resistance, and then find the voltage or current. And so voltage sources, and you can simplify by combining voltage sources, when they're opened up, become a short. And a current source, when you open it up, becomes an open circuit. And so to find the equivalence of some arbitrary circuit, you would want to open up the source and see what you have. So if we have a Thevenin voltage, what we're saying is to open that up between a node A and a B, we're looking for this voltage looking in right here. We want to find the resistance. Sorry, we want to find the resistance looking in, the resistance between those nodes A and B, and that would be the Thevenin source. So to open that up, we would turn this voltage source into a short, so we just make it a short circuit. So, and the best thing to do is just redraw the circuit. So redraw it as a short. There's a voltage source in there, but we're trying to find RTH between nodes A and B. That's a short, right? between these kind of two nodes there. We have RTH, and when we look in, we just see RTH. That's the only resistance that's in there. It's in, but between these two nodes, all we see looking in is RTH. So it's easy to solve. And it's not that much harder when we have more complicated circuits. And how does that work for a current source? So if we have a Norton Current source, and we have a resistance, and I'll call it RTH, between A and B, and we're looking in between. We want to find RTH, so we'll open up the current source. Opening up the current source means we just turn it in and open. So I'll draw it as if it was still there. We would open it up. Oops, that's not where it is. Let me make sure and just erase what I need to erase. So I would draw it as opened up. What's that? Pin. A and B. We have RTH, and that's an open. Right? We just replaced the current source with an open circuit, and looking in, all we see is that Thevenin resistance, because there's no connection here. We don't have any connection here. It's an open. So looking in here, we just see this path here through RTH. Hopefully I have this set up so that you can, the video will just pause and give you some examples to work. If you feel pretty good about them, then you can just click through one and do it real quick. But if you don't, it'll keep giving you different versions. And I'll try to have a Thevenin and Norton circuit of some kind. Solve them. It should stop up by itself, and then rejoin it here after you click restart. So we can use Thevenin and Norton, that system of opening up and shorting sources to find the resistance as a way to simplify a more complicated circuit. So obviously just a Thevenin source by itself is maybe too trivial. But if we have a more complicated source or circuit, and I know you've got various systems that you can use to solve this that would work just as well, or you might feel like they'll work quickly and more easily, and for you right now they might work more easily, but I guarantee over time you'll forget it, and over time you'll remember this, or stand a better chance of remembering this. And so how to simplify this, that's kind of a pain, because we've got something in series and we've got something in parallel, and looking in here, it's a nuisance. It's a little effort, but it's not too bad. In fact, if you look at this, you can realize, oh, right here, this is a Thevenin source. If I converted it to a Norton source, maybe it's a whole lot simpler. The basic rule I would use to look at simplifying circuits is look at them. If you don't see any simplification you can do, then change something, a Norton into a Thevenin or a Thevenin into a Norton, and see if you can simplify it. And sometimes you won't even understand how you can simplify it until you've done some simplification. That might sound really wacky, but it just is how it works. So I'll take this this Thevenin source V1 and R1 and make it into a Norton source. So V1 over R1 would be that equivalent current. And now we have R1. This would be the Norton equivalent of this, just this part of the circuit right here. That Norton circuit is right there, but it connects through this node to these two, and it connects through this node to these two sides, basically to A and B, so I'll draw those farther out. So this stuff is all in parallel now.